So now that we learned the procedure for the method of joints, we can initiate our first simple example. And here we have an example that asks us specifically to use the method of joints. That's very important later on when we understand also the other method, the method of sections, that we clearly differentiate which methods we're using. And particularly here we asked to find all the member forces. And let's take a look at the structure first. We have pretty much the simplest truss system that we can ever think of. First of all, it's a single triangle with a 45-degree angle. And we have node A and C that are supported. And then node B is an independent one. So if you paid attention in the previous section, then you know that we could technically start this problem without solving the support reactions, because if we cut node B up here, we only would have two unknowns and we could solve this. But since it's the first problem that we're solving, let's actually focus on the support reactions first and then move our way in so that we're following the official procedure that we developed before. So first of all, I have RAY here and I have RCY on the right side, and A also is a support that is pinned, therefore I have a support reaction as well. And instead of pointing it to the right side, I immediately point that to the left side. That is RAX, and I don't have to run any complicated calculations. I already know that that is equal to 500, simply because the external force is 500 here at node B, and it has to balance here because that's the only thing that can balance my support reaction. So now I can calculate all my other support reactions. Let's just calculate RAY and RCY. So to calculate RAY, I need to take the sum of the moments about point C to be equal to 0. And as always, counterclockwise positive. And 0 is equal to, I start with my unknown, RAY. So RAY here turns about point C with a distance of 2 meters. So times 2 meters. And that is a clockwise rotation, therefore that's negative. Now I would think that I have to include the 500 support reaction, but its line of action passes through the point of C, so I don't have to worry about this. So the only other one I need to worry about is this one, which also happens to have a distance of 2 meters. So there's 500 Newton multiplied by 2 meters, and that turns clockwise, therefore it's also negative. And when I solve this, I find that RAY is equal to negative 500 Newton. And all that means is that we end up with 500 Newton downwards. So that makes perfect sense. In reality, RAY has to go downwards with 500. Because if the system is in balance, then here this is the 500 Newton up here is rotating about this point, and the only thing that can put that back in balance is this 500, and they both happen to have the same lever arm, which is why the values are also identical to each other. So now, simple enough, I can use, or I can find RCY, in this case by using the sum of the forces in the y direction being equal to 0, and therefore RCY is equal to 500 plus 500 in the upwards direction. Why is that? Because the only vertical forces are these two and they have to balance each other. Therefore, RCY must be opposite to RAY. So now I have all my support reactions and I can move on to following my method of joints. Now, let's look at the system here. And as I said before, we can either release this node here on the top, but then we wouldn't need our support reactions. So let's actually take advantage of the support reactions that we calculated, so I can start with my node C. In this case, I could have really started anywhere, because any cut that I can possibly make right now would only include two unknowns. And remember that for the method of joins to work, we need to have a system with no more than two unknowns. And this is the case here for all of them, for all of the cuts. But I will simply start with node C, just because it gives us a good introduction into the problem. So the first thing I do is I cut joint C, and remember that the first thing I do is I draw a free body diagram. So let me draw the free body diagram of node C. So my node C looks like this. And I cannot forget my support reaction as well. So that was 500 upwards. And now in the second step of my method of joins, I need to assume a direction. Remember that we initially assume everything being in tension. So the node C here is in tension. So that means that AC would be pulling to the left, and CB, or BC I should call it, BC is pulling to the upwards left. Of course, this cannot be in balance, right? So let's look at that. If this is pulling to the left and this is effectively also pulling to the left, that doesn't work. And it's probably already easy to see that this 500 here cannot be balanced by the vertical component in BC if BC is going up. So in all reality, my equation then would write as follows. Sum of the forces in the y direction is equal to 0, upwards positive, and 0 is equal to, and now I'm going to use a little sketch help here. I have a vertical component and a horizontal component, and the vertical component would be BCY, and then here we would have BCX. And currently they both point in this direction, but we will soon learn that this is incorrect. So 0 is equal to plus BCY plus 500 Newton. And if I rearrange this equation, then BCY is equal to negative 500. And really what that means is that we have 500 Newton going downwards. And so now I have to correct my sketch here on the left to stay consistent. So I will erase this now. So my arrow direction actually is incorrect, and therefore I have to flip it around. So let me start with the blue dashed line again. The first thing that I know is BCY is going down. And now by default, BCX needs to go to the right, and BC actually needs to push on the node C. And now it's a 45-degree triangle, so therefore it's very easy for me to understand what happens next. So BCY is equal to BCX, and therefore BCX is equal to 500 as well. And that, of course, now is pointing to the right side. So now that I know that, I can do one of two things. I can either calculate BC first, or I can set up the equation in the x direction. But I think it's better for us to calculate BC first. So because of the 45-degree angle, BC is equal to 500 times square root of 2. So the square root of 2 is simply coming from a triangle that is 1, 1, and square root of 2, right? That's a 45-degree angle here, for those of you who have never seen that before. But ultimately, that is what our result is. And that happens to be equal to 707 Newton. So that's actually a result. So therefore I can double underline this. So this is my BC. And now I can move on to the next one, which is AC. So how do I calculate AC? AC I calculate by the sum of the forces in the x direction being equal to 0. And 0 is equal to minus AC plus BCX. And keep in mind, BCX is equal to 500. And therefore I know that AC is equal to positive 500 Newton in this case. And what that means is that we assumed the tension to be correct. So that's actually my last step I have to do now. So I have to say, hey, this here is in tension. And then my 707 is actually in compression. And so far, so good. This is definitely something we could have understood from just following the theory. But now the challenge is for somebody who has never dealt with these problems before, how do we translate this to the next node? And so I'm going to do that next. So I know what's going on at node C now. That means I can translate it to any other node. But for educational reasons, I go up to node B now. So let's cut node B. So maybe I'll do that here on the right side. So cut joint B, and joint B looks as follows. We have a vertical member, we have the diagonal member, and we have the horizontal force. And the horizontal force was equal to 500. And so we have BC here, and we have AB here. And remember, AB is an unknown, so I assume this to be in tension, but BC we already calculated before, right? So BC is actually the 700 something, right? So I should zoom that in here. So we already calculated the value for BC. And notice that here BC is pushing on the node. And it is very common that students now think to push towards the node, or like actually is going diagonal downwards. So therefore my arrow here has to go diagonal downwards too. But that is actually incorrect, because keep in mind that this arrow here for joint C said or stated that this is in compression. And if this node is in compression, or if the entire member is in compression, then everything up here has to be in compression, including the node here on the top. So therefore, my BC actually has to push up, which on the first glance seems a little bit counterintuitive because it's exactly the opposite direction. But keep in mind that there's actually a member in between, and the member in between, I'm just going to draw a part of it, would be this guy here. So it would actually be BC. And now that also needs to be in compression. So how do I show that that member is in compression? I show that like this. And so what I have effectively done is I have cut the member here and also here. And therefore I now can reason that my arrow up here has to point upwards. So that makes our life once again very easy, because our system is so simple in this case. So I can include my components, which I also already calculated those. In fact, they are 500 and 500. And you will see in just a second that that makes perfect sense. So this here was BCX. And remember that BCX was effectively equal to 500. Also, BCY was equal to 500. But before we talk about the y direction, let's look at the x direction and notice that this 500 here balances this 500. So let me write down that equation just for educational reasons. In an exam or so I would never do that, but I would clearly for the node C write down an equation that says sum of the forces in the x direction being equal to 0, to the right positive, and 0 is equal to plus 500 minus BCX. And so you see, if I would have started at this node, I would have gotten the same result, right? So if I would have started with joint B, I would have found that BCX is equal to 500. And then I also would have found that BCY is equal to 500 because it's acting in the 45-degree triangle. And so now I probably don't have to tell you anymore how AB is calculated, but AB is just calculated by the sum of the forces in the Y. So I'm going to do that for educational reasons. Sum of the forces in Y is equal to 0. And 0 is equal to minus AB plus BCY. Once again, that's 500. And so therefore I know that AB is equal to plus 500, which in this case means that it's correct, that it's going downwards. So what that really means is that this is in tension. So I need to identify that. And by the way, up here, like for the previous one, we also would have found that BC is in compression. And remember here that, yeah, we wouldn't find a negative answer to this equation, but that's because here we already assumed the node to be in compression. So now I've calculated effectively all my forces, all three member forces. The last thing I need to do now is to draw it in a diagram. I'm going to do that here on the top. So on the top right, I will draw my system, and I have, keep in mind, always the way that I show these cuts. So I have the corner here, the member, and the other corner. And then I have to connect the corners. And I have another member here. And now let's look at that together. I need to identify what is compression and tension. And I started with the node on the bottom right, node C. So I'm going to also include my forces there first. So I found that AC is in tension. So AC is in tension, which means it's going in that direction, whereas BC was in compression. So that's how the very first result was. And now I can continue this logic. So I'm going to start with AC, and I put this component in tension, and I put this part in tension. And the way I show that is first the inner part, the member, is in tension if I do it like this. And on the other side, it has to go like that. And the value we found was 500. So 500 Newton in tension. Now let's move on to BC. BC is the diagonal member, and BC I found to be 707, right? Remember that from down here. So 707, and that was in compression already, but I can put 707, and I can already say it's in compression. But now I need to show my arrows in the right direction. Once again, here it's pushing on the node, so here I have to be pushing on the node as well, and here I have to push towards the member inside. So the way to properly show that would be as follows. It looks a little bit strange the first time you see these arrows here, but it is correct. So now they are in compression. Last but not least, I have the vertical member, and that was also 500, but that was in tension. So I'm going to put my number here first, 500 in tension. And if I know it's in tension, then it's pulling away from the nodes. And for the inner part, it's pulling away from the inner part, or from the member, I should say. I probably shouldn't forget my support reactions or my external forces. I need to include those too, otherwise the system cannot be in equilibrium. So I have these two vertical support reaction. I have one horizontal support reaction and one horizontal external force. So this was 500. And then I had 500 here, 500 downwards, and 500 upwards. And that is the complete diagram. And this is really what you need to do. Of course, the problems become a little bit more convoluted than just these three examples or the three members here. But this gets the point across very well for like a beginning problem. And I think with this, we now are able to solve method of joint problems. So now I will leave this next problem for you and for your groups to solve. This is a very interesting problem. Let me just give you an introduction to it. So there's a pin down here and a roller down here. And you see there's, our triangles effectively. So I have a first triangle here. I have another triangle up here. And effectively I have a triangle here as well. And two external forces. So what would I do here? I would find my external forces first and then cut my way around the system and work my way in. But I leave this for you and your study group to practice. And I will actually go ahead and solve this problem with you or for you. So let's look at it again. As everywhere in this lecture, we're dealing with the method of joints, not the method of sections. And now we are asked to find all the member forces. And I will now show you how to do this. We could technically start our way from the left to the right, although we do have support reactions here on the right side. We technically do not need to calculate these because this is acting like a cantilever system. And I'll show you what I mean by that in a second. But I probably have a support reaction that goes in this direction, support reaction that goes in this direction, and a support reaction that goes in that direction. So I call this here RDX, RDY, and RCX. And if you look at it, so this here could be like one complete member, and it would be a cantilever because it would be like fixed here on the side. And remember from our internal forces for rigid bodies that we always could work our way in towards the cantilever without even calculating the support reaction. So this is kind of similar here. I can work my way from here all the way into the system. And then I can use my support reactions to actually understand if my answers are correct or not. So let's do that. So let us actually start by cutting the system at node A. So cut node A. And the way I do that is by copying my geometry first. And of course, geometry can be tricky with these problems sometimes because it's easy to overlook like a distance or a length. But here in this case, I have a 3-3 triangle, if I'm not mistaken. So let me include the 200 here. So this is 200. And once again, it's a 45-degree triangle. That will make our life very easy in this case. But remember that I assume this being in tension. But before I assume the other one to be in tension, I will actually solve this first. So I have not RAY, I have AF, AF, AFY, and AFX. And you already see that if I use the sum of the forces in the y direction being equal to 0, then I will find that AFY must be equal to plus 200. So that means that AFX is equal to also plus 200. And now I know that my 200 here is actually pulling to the right. And the only thing that can balance this is AB here. So let me include that. AB. And AB, of course, has to push in now. So I don't even assume it to be pulling away from the node. I know that AB and AFX are equal to 0. And so therefore AB is equal to 200. So let me write that down. Sum of the forces in the x direction being equal to 0, positive to the right. 0 is equal to minus AB because it's going to the left, plus AFX, and AFX is equal to 200, and therefore AB is equal to plus 200. And now I know that one of them is in tension and one is in compression. In fact, the 200 is in compression, and the other one, AF, I haven't even calculated yet. So AF is equal to square root of 2 times 200, and that is in tension. And if I solve this, I will find that AF is actually equal to 282.8 Newton in tension once again. All right, so I have my results at node A. Let's move on to either node B or node F. And if you pay closely attention, you see that I have now this member solved. So if I cut node B, I have one known, but 1, 2, 3, 4 unknown, and therefore I cannot solve it. However, if I move up to node F, I have only 2 unknowns, which would be FE and FB. And so I can actually solve that. So let's move on to that node. Let me draw, or let me write out what we're doing. So we're gonna cut node or joint F. And if I want to draw that cut, it's going to look like follows. I have the diagonal member, the horizontal member, and the other diagonal member. And I cannot forget about my external force. That's a very common mistake that or easy to overlook, I guess I should say. So I have a vertical force here, which is equal to 500 pounds, by the way. So I need to fix my newtons. So let me fix that here. That's actually in pounds. But the concept stays the same. I also remember that my AF, so this here is AF was in tension if I'm not mistaken. So AF in tension means it's going downwards. And now I have to decide what I do. But to make my life easier, I'm going to put in my components. So I have these components. Of course, they go to the left and they go down. And I believe they were actually equal to 200, and then here also 200. But I also have other components now. And I can almost do this visually now, so I'm going to use a different color to make this very clear. I have this vertical component and I have the horizontal component. So the only thing that can happen now in the vertical direction that balances this 500 and this 200 down, which together they are 700, the only thing that can balance this is my vertical purple line here. So I don't even have to really write out my equations anymore, if I really understand this. I understand that this must be 700. So that is 700 due to the sum of the forces in y being equal to 0. And now I'm still dealing with a 45-degree triangle there. So the distance from here vertically down was 3 feet, and then from here to the right was also 3 feet. So therefore, I know that all my numbers here are also 700. So it's pushing in that direction. And the last thing that I know now is that it has to be in compression. And if I'm not mistaken, this member was called BF. And BF is equal to square root of 2 from the 45-degree triangle times 700. And that is equal to 989.9 pounds. So now I have calculated that component as well, but I'm lacking the horizontal component, and I'm going to use a different color for that one as well, just to differentiate that. So it's this guy, which now I'm going to solve visually again. Why can I do it visually? Because BF is pulling to the left and AFX is pulling to the left. So this component here, which would be EF, has to pull to the right. So let's do that. EF. So this must be in tension, right? So EF. So what is EF equal to? EF is equal to 700 plus 200. And this is already applied the sum of the forces in the x direction being equal to 0, right? So that's where that's coming from. So we know that EF effectively is equal to plus 900 pounds, and that is in tension. So that is in tension, and by the way, let me not forget that BF was in compression. All right, so at this point it's probably best for me to start beginning with my sketch. So let me draw that sketch in a somewhat bigger fashion up here on the top right. So I have the horizontal member on the top. I have the horizontal member on the bottom. I have the diagonal members. And I have them in both directions. And then I have the vertical members. And of course I have support reactions, but before I do that, I include my external 500, and here we have 200. And now I'm going to zoom in and erase the portions that I don't need for my diagram, or like I'm pretty much erasing the cuts into the system. So I have a cut here, and then I have ultimately cuts here. I have cuts right up here, this node, and this node, and that node. And the ones that I already calculated are the ones on the far left, and I have to, of course, find my answers here. So AF was equal to 282. So AF was 282. 282. And then the one on the bottom, AB, was equal to 200. And this was in compression, and this was in tension, by the way. And in my node F, I found that EF is equal to 900. So I'm going to have to zoom in for that. 900. And 900 was in tension. And my other component was 989. So I'm going to call that 990. And that one was in compression. And before I move on now, I'm going to include again if it's in tension or compression with my arrows. So 282 was in tension. That means it has to go in this direction. So 280 in that direction. Compression is the other way around. This is all in compression now. And the 990 is also in compression. And last thing I can do here so far is the 900 being in tension. And that's all I got so far. So, but now I can use this to be less confused. So next up, I can either cut, let's take a look at it. I can either cut node E, which is probably easier, than node B. And we will find something very specific about member EB in this case. So, but let's cut node E to look into that. So I'm going to tell myself to cut node E. And what I have, structurally speaking, is a system that looks like this. And you will see how simple this becomes in a second. And don't forget, the one that I calculated was this one, which was EF. EF, which was in tension with 900. And in tension. And now let's look at the other two ones that we have. We have EB and we have ED. And there's a very important observation in this. This is very helpful for what we're going to talk about in more detail next lecture. But this member here is the only thing that acts perpendicular to these two members which are in line with each other. So EF and ED are in line with each other, and we have a third one joining them. So what that means is that if, in this case, these are perfectly horizontal or directly in the x direction, and so the only thing in the y direction is EB, because let's look again at the actual sketch of the problem. See that here at E, there's nothing external, right? So there's no force. So what that means is the only thing acting in the vertical direction is EB. So if I were to write an equation for that, so the sum of the forces in the y direction is equal to 0, then 0 would be equal to plus minus EB and nothing else. And so therefore EB is equal to 0. And in fact, this is called a zero force member, right? So this is a zero force member. And if you have a little bit practice, you could have seen that from the get-go, because you will notice once again that here you have two parallel members that are joined by a third one, and that third one has no force at the external node, right? So it's an empty node that connects two parallel ones and a random third one. And so therefore, this must be a zero force member, right? So you must have this as a zero force member. So effectively, this thing is actually not there. And in fact, I will now erase that in my result sketch. So I can now remove this component here. It's not there. Believe it or not, these zero force members exist, not only to confuse students, but in real life they exist for like either construction stages or for relocation of forces and for different force flow, and sometimes for redundancy. So, but they do exist, and I challenge you to go out next time you see a structure and identify all the zero force members. But we'll talk more about them in the next lecture. Now, just as easy as it was to find the zero force member, we also know that ED must be equal to 900 now, right? As a consequence of nothing else happening here, and that those two are being parallel to each other. So I can say that the sum of the forces in X is equal to 0, and therefore ED is also equal to 900 in tension. So this is not a big surprise. And in fact, if I zoom into my sketch here on the top, it's almost pointless now that we erased the vertical member to have these arrows here. So I'm going to remove them, and I will make them just one big long member, if you will. So let's look at that. So I really have only this, and now I know that everything up here must be 900, and here this must therefore also be in tension. So I'm already done with that component now. So last but not least, I can either now focus on this node up here or on this node down here. And I think it's easier to start with this node. Well, actually it's not easier because we don't have the support reaction here. So let's move down to the node down here, which is actually node B. So notice that because I have calculated the or I have kicked out the zero force member. Now I have only 2 unknowns left, so I can do that, right? I already calculated these 2, I eliminated the zero force member, and now I can focus on these 2. So let's look at that. And maybe for simplicity, I'm gonna use this spot here, and I'm gonna cut node, well, I'm using blue for that, cut node B, and node B looks as follows. I have the horizontal member, I have the first diagonal member, and I have the second diagonal member. The zero force member is gone, and the last one. And now I need to be careful because I need to bring over the values. So AB was in compression with 200. So this here was 200. And then we have 990 also in compression. So 990 here. And now the question is what happens at the other ones. And I think instead of really going into big depths here, I'm going to do it visually as well. So I have this component and this component. And by the way, that's also true for my other member here. This one and this one. And what I have now is easy to observe that no matter what this value is, I don't remember this right now, but I will look this up in a second. Whatever this value is plus this 200 can only be balanced by this and this. And this here is the only thing that pushes down. And whatever that is, it can only be balanced by this guy. So this is where I start. I start with the sum of the forces in the y direction. So I already know that my force here has to go up. And that member I need to look up is called BD. So BDY and BDX. And so BDY must be equal to what was the other member? BF. So BFY. So now all I need to do is find BFY. Where did I calculate BFY? I did that right here. So that's 700. So I know that that is equal to 700. And now I can use that to also find BD. So BD now by default also must take on that value of square root times 700, which is equal to 990. And that is in tension. And so now I can focus on the horizontal direction. And to do that, I'm going to use a different color here. So I now have to decide if this is going to the left or to the right. But I can already see that BDX is pulling to the right, this one here is pulling to the right, and the 200 is pulling to the right. So I can 100% already know that my reaction here must be towards the node. So this is definitely in compression, but by how much we have to see now. So let's collect our values. First up, BDX, and I believe that was 700. And then we also had the horizontal component here, which that was also 700. And now I have 700 plus 700 plus 200. That means that now I am dealing here with 1600 in compression. And now I solved effectively all my forces. So let's look at that. Let's go to our problem up here. So that was compression of 1600 compression, and compression means pushing on the node, pushing on the node, pushing on the member. And my diagonal member was 990 in tension. So 990 in tension. Tension means pulling on the node, pulling on the member, pulling on the member, pulling on the node. And now if you paid attention, we have one more zero force member, which is exactly here. Why is that? Because BC and RCX are actually in line with each other. So you have a third one joining here, but there's no force that's pushing anywhere vertical relative to this direction. So therefore, CD must also be equal to 0. And so I can actually erase this here. So my system actually looks like this. And last but not least, for full equilibrium, what I need to do is include my support reactions. So remember that I have a support reaction that's going in this direction and one that's going in that direction. And we also have one that's going up. And we can already tell that the one that's going up must be 700 because that's the external force equilibrium. And then I can tell from this part here that I must have 1600 here, and therefore this one also must be 1600. So 1600, 1600. And that is the complete solution. And I leave it up to you now to go ahead and actually check this node for equilibrium. If I were you and I would practice this method of joints, I would go ahead and draw out this node and check if these are in equilibrium. So there's a horizontal component here due to the diagonal component. This one is purely horizontal. And then I have the 1600 here to balance that. And you will find that that will actually come out to be the same. So that concludes our problem. Let's take a look at all of it, what we've done. Please note that I sometimes took some shortcuts here based on the geometry. So it always goes a long way to draw a free body diagram. And remember, you have done this before when you calculated the tensile forces in cable structures. Now with trusses, you have the advantage or disadvantage, depending on how you look at it, that they also can be in compression. So you see compression members everywhere in the system because these are stiff members now, not like cables that cannot be compressed. And the ultimate goal for all of these problems is to represent your results just like we did here. And I believe you now have all the tools to solve these problems, and I wish you good luck with that.